Hello everybody, welcome to the Geo Shed. It is about 46 degrees Fahrenheit in here, which is about 8 degrees centigrade plus or minus. Today I'm going to be talking about normalization, but what you can probably see is a little bit of breath here. You can see your breath around 45 degrees Fahrenheit, so it's a little chilly in here. To most people, I'm used to it, doesn't bother me. But what do I heat this place? Yes, I just started heating it this morning, so I don't have, it hasn't had a chance to really get going. I have two heating things. You can hear the one in the background. Actually, you might be able to see it. I have that electric heater right there, and I have a propane buddy heater, which is meant to be for indoors, which I actually run off these. We do have 20-pound propane tanks. One is in the storage shed, but it's empty, and the other one's up north. So these don't really last. It says on low they could last 6 hours. These last me like maybe 3 to 4, and 4 on low, 3 if I have it on high. But anyway, it's cool when these start to run out. It's already melted, but maybe you can see it's wet. This actually frosts on the bottom. But anyway, before I ramble too long about that, today's topic is normalization. As you can see on the board behind me, why is this important and why is it relevant in geology? Well, I am going to get closer to the board and show you some examples and stuff, but basically normalization is used in geology when plotting on 2-point ternary diagrams, but using 3 or more points of data, or 3 points of data actually. And we do that on what we call the quartz, alkali feldspar, plagioclase, feldspathoid, or foid diagram, or QAPF for short. The QAPF diagram is basically two ternaries, one right side up, one upside down. And you only use one at a time. The thing about this is if the rock has any quartz in it, and I've said this before, if your rock has any primary quartz in it at all, you're going to use the QAP part, or the top part of the diagram. Why is that? Because feldspathoids and quartz cannot form in the same rock. Quartz is the last thing to crystallize out of a magma in Bones reaction series. If you still have abundant other elements in there, the magma is going to want to form those before it forms quartz. So it's a chemistry thing, okay? So you can't get primary quartz and foids in the same rock. Okay, but if you do have foids, what you're going to use is you're going to use the FAP part. Okay, get the jokes out. Anyway, you're going to use the FAP part, or the bottom part of the QAPF diagram. And it functions just like the top part, except for illustration purposes, it's flipped upside down. If while you're computing, you can't do it, because there's no such thing as negative quartz. You're not measuring a negative number. That's not why that bottom part is there. And that's what you would be, because quartz is measured on the horizontal in every instance. All right, it's the first thing you're going to normalize for. So you're not working with negative quartz. You're working with positive foids. You can't have less than no quartz. All right. So you can, if that confuses you a little bit, the fact that it's upside down and that the 100% is on the bottom instead of the top, just flip the triangle over. That's all you got to do, and then you can work with it just as you would a QAP part. But we usually you only see the QAP part in online and stuff like that. Why is that? Because quite honestly, almost all plutonic and aphanitic rocks have some quartz in them. It's rare for them not to. Probably 95% of rocks derived from magma or lava contain quartz. But even here in the Midwest, we do have foid-rich rocks, and I've shown you those before with my sodalitic cyanites and things like that from collecting on the beach in in the UP along the Keweenaw, and that's derived, and those rocks are mostly derived from the Coldwell complex in Ontario, which I have found existing in veins along Trans-Canada 17. I've done a video on that from last year, and some of the Foyd-rich plutonic rocks may have come from as far north as Greenland, as in the case of my naugite, which is a local term in Greenland. At least I think it's naugite. It's actually a Foyd-bearing syenite. So I'm going to show you how to actually normalize, and then I'm going to show you how to do it on the QAPF diagram. I'm not going to explain all the plots on the QAPF diagram for you, or what the difference between a tonalite, a granodiorite, a granite is, and you can subdivide granite, but you don't have to. I'm not going to explain all that. All right, that's a talk for another time, and it would make this video way too long. It's probably going to be over half an hour as it is. But anyway, let's get started on this. Okay, so what is exactly normalization? All right, it's when you're taking usually a percentage, and that's what we're going to work with here, because when we plot on the QAPF diagrams, that's what we do, is we plot percentages. But we're taking a whole, or 100% of something, excluding one of those parts, or some part of that 100%, and resetting everything that's left to 100%. Why would we do this? Well, because in plotting on the QAPF diagram, we don't worry about the mafics in a rock or something like that. Okay, so we exclude them because they're not used in the classification. In the QAPF diagram, we are plotting three things. Okay, we are plotting quartz or Foyds. We are plotting alkali feldspar or K-spar, and we are plotting plagioclase. But I can tell you every rock's going to have some mafics in it. What I mean by mafics, dark minerals essentially. Pyroxenes, iron minerals, olivine, that kind of stuff. It's not included. We take it out. Okay, I have 4 markers. We'll say this is our mafics. We'll say, doesn't really matter at this point. I'm probably going to confuse them later anyway. We'll say this is our quartz, this is our K-spar, and this is our plagioclase. All right. So these are our mafics. They make up 100% of our rock. We have 4 here. Each aspect, 1. We have 4 components, so we have 4. Okay, and each one of these is its own aspect. So each one represents 1/4, which equals 0.25. You multiply that by 100. Equals 25% of our markers. So each one of these is 25% of my whole, which is 100. Okay. Now we are going to take out the mafics. Now I have to reset everything to 100%. All right. So now I have 1, 2, 3 equals my 100%. All right, so I have 3. And in this case, I still have 1. All right, so each one, I have 1 for quartz, 1 for K-spar, 1 for plag. So it's the same thing as it was before. We still have 1. 1 divided by 3, which equals 0.3 repeating. We're going to round. You should save as much round. You want to carry this stuff as many decimal places as you can while you calculate. I recommend 5. All right, but and save your rounding to the end. You shouldn't round while you do this because it can jack it up. And I'm going to show you what rounding while you're doing it does, because I'm going to do it to show you. All right, but anyway, 1 divided by 3 equals 0.3 repeating times 100 gives us 33%. And that's 33% for each one, because they're in the exact same amount. Okay? That is basically how to illustrate normalization in a 2-step process from our original to this. All right, and that's what we're going to do for the QAPF. Okay, many of you may be familiar with the USDA's textural chart. That's a 3-point plot. This requires no normalization at all if all you have is sand, silt, and clay. And if you have gravel, you only have to normalize once, like with the marker example, taking one away once to normalize. All right? But the QAPF doesn't function like that. All right? And there's you sometimes online you'll kind of see that 3-plot diagram used as a background for the QAP or QAPF diagram. It's incorrect because you're not doing a 3-point. You have to normalize when you plot on the QAP. No matter what, it's going to happen. The USDA textural chart, you do not have to normalize if all you have is sand, silt, and clay. And I'll take you through an example of the USDA chart and how it differs. Okay, here is USDA textural chart. It's typical, it's online. This stuff is free. It's not some big secret. You can find it. Okay, so how does this differ? Well, it looks like a triangle, right? And I said that with the QAPF, you're just using one triangle or the other. So why is it different? Well, because we're going to go through a specific example here. It's a 3-line plot. So we'll say you have sand, silt, and clay. Sand is 33%, silt is 20%, clay is 47%. You add that up, that equals 100%. Now, what do I mean by how do you derive these percentages? Well, in a rock, it's kind of hard to bust it apart and to actually get the mass through weight, although you can do that with weaker rocks like sandstones and stuff like that. But in like a granite, it's hard, so you use visual volume, right? But in a soil chart, you can break up the particles and actually run them through sieves like these. This is just part of my sieves. The meshes decrease in size as you go down. So you can actually get an actual mass. But, all right, I said that. Now let's get back to the sand equals 33%, the silt equals 20%, and the clay equals 47%. All right, no normalization is needed here. It's not necessary. We have no gravel, right? So what you do is you plot each one from your 0 following one of those triangles. You see these little triangles within the big triangle, following those lines. And in this case, they're in 5% increments. You have to read in between the lines, so you can just work with whole numbers. All right. So you plot your sand first. It's on the bottom. You go 33% from your 0. You draw your line. All right. Then you do the same thing for silt and clay. If you find this difficult to do, they should all meet at one point, as you can see here. This yellow circle is where they all meet, and that is where my soil plots, and it plots within the clay. Now, if you're doing this and they don't all meet at one point, you're doing it wrong. The easiest way to do this manually is do put what you're doing on the bottom. So you're doing your sand first, and the sand is on the bottom. All right, you get done with your sand, then you rotate the chart to do your clay. Put the clay on the bottom, then put silt on the bottom. All right, that's the easiest way to do that. And in this case, you come out with clay. There are essentially 2 QAPF diagrams we work with. We work with a plutonic version, which is rocks that are crystalline to the naked eye. And we work with the aphanitic rocks, which have no crystalline structure or consistent crystalline structure visible with the naked eye. There is an official line to put, but generally that's what they are. And plutonic rocks tend to form deep underground, as where aphanitic rocks tend to form close to the surface or on the surface. Those would be your basalts, your andesites, your rhyolites, things like that. But you can't get dikes of these things. And your plutonic rocks would be your granites, your tonalites, your quartzolites, things like that, your cyanites. This is a plutonic rock from Wisconsin. I've done a video on this. This is the one with Rapakivi type texture. You can see the minerals. Just look at the colors. You can see they're visible with the naked eye. As I move it around, you can see the light reflecting off of it. All right. So that's a plutonic rock. An aphanitic rock, this one's weathered. I apologize. See if I can find a fresh surface. Yeah, I can. Is a basalt. This rock is almost all microcrystalline. It means you can't see the crystals with the naked eye. Now, is there anything in between? Of course, kind of. Here's a rock I am currently testing. And you look at it, let me get the better one, the fresher surface. You look at this here, and you're like, oh yeah, that's gotta be plutonic. I can see, definitely, unquestionably see very large crystals in here. But there's microcrystalline too. And if you can see it very well, that's, in this case, we call the microcrystalline ground mass, and the ground mass makes up most of the rock here. These large crystals are what we call phenocrysts. All right, this rock is igneous, just like the other two I just showed you, but this started to crystallize underground. You get bigger, that started to crystallize, you get these phenocrysts. And there's some black mafics in here, they're real tiny too, but then it got pushed up to the surface. And when it got pushed up to the surface, it cooled a lot quicker, and you got the microcrystalline ground mass. So this is technically aphanitic and not plutonic, even though this forms slightly underground. How do we classify that? That's honestly a nomenclature thing. But like I said, these are phenocrysts. They didn't cool out of the whole body of the magma. All right, they crystallized first, were forced up, and then the rest crystallized really, really fast. And the ground mass makes up more. Yeah, I had to sit here and do little areas under the hand lens and look at it, but it does make up typically more than 50 to 55% of the rock. So it's aphanitic with phenocrysts. Okay, so I've shown you those. Let's get back to the QAPF stuff. I am going to take you through an example of how to do a QAPF plot here. First of all, there's some requirements to use these charts. The rock has to be igneous. The rock has to be, well, crystalline. What I mean by crystalline is it could be microcrystalline, like a basalt, or rhyolite, or an andesite, but we exclude ashes, things like pyroclastic flows and stuff like that. Those actually have a different ternary plot, and that's a talk for another time. So we exclude those. The rocks have to be greater or equal to 50% of the rock plus or minus 5%. So your rock has to basically be 50% crystalline, greater or equal to plus or minus 5%. Why this? Well, because like I showed you there with this rock, this is really close to 50% phenocrysts, 50% ground mass. It's a call, right? There are some places in here where the rock is 55 to 60% ground mass. There's some places where it's 45. But overall, it's dominantly ground mass. So I'm going to use the aphanitic classifications. And this actually comes out to be a phonolite or a trachyte because it has voids in it. So we would use the bottom for this. And I've already done the analysis on this. I'm going to show you a normalization for a QAP plot only. So we're going to be using the top part of the QAPF diagram. So there's a fourth requirement. The rock cannot have voids in it, and I've already explained why. So let's get into this. Here's our example. We are going to use a rock that's 29% quartz, 34% alkali feldspar or K-spar, same thing, 11% plagioclase, 26% other. That'd be your mafics like your pyroxenes and your olivines, stuff like that, and accessory minerals like hematite, epidote, calcite, etc. Yeah, I do have note cards. I'm trying to get this somewhat organized to keep the alrights, buts out, because that's something that someone brought up before, and I am pretty bad with that. All right, so let's get to this right now and show you the diagram and show you how to normalize. Okay, so here comes the maths. Like I've already said, here's our percentages. You do not see the O, the other. We've gotten rid of that. It's done. All right, because we're not using it. So there's basically two equations you can use to do this. I have quartz initial, K-spar initial, plagioclase initial, and then you'll see an X in my X initial. What the X initial is it just means any one of these at any time. All right, but you got to be consistent. You're not changing because that's only an X, so I don't use a Y. So actually, it would probably be more appropriate if I did this. if I did this for each. Put a y at the end. All right. Well, these are actually the same thing. All right. When I'm normalizing, see I have 100 on the outside here. Here I have my x initial. Basically here what I'm doing is I'm pulling this out. And in order to do that, I have to drop this back in here so I can use this as well. And I'm going to show you both of them work. I use this one. I use number 2. Just because it's easier for me to calculate that way with my calculator. This is easier to do on a calculator than this is. So, but you can use either one. And then the marker diagram, and in the marker example I showed you in the beginning there, I was using this one. This would be my 1, this would be my 3. All of this would be my 3. And technically, I guess, this should be like this. Technically. So, because you add these first. Order of operations. I apologize. Okay, I've redrawn that. Hopefully that looks cleaner for you now. So there's your first equation. There's your second equation. So let's calculate. So let's use our quarts first. Okay, and we're using equation 1. That's what this number 1 here is. So we're going to use our quarts. And our quarts initial is 29%. So we take 100, all right, and we take our 29%. That is this X initial here in this case. And if we were doing alkali feldspar, we would use A initial. And if we were using plagioclase, we'd use P initial. So, but we're just going to use quarts. I'm going to show you how to do quarts. So 100 will eventually be multiplied by our X initial or quarts here, divided by all 3 of these added up, which is 74%. So 29 divided by 74 times 100 gives us 39.2%, which is equal to just our quarts. Okay, we've normalized for our quarts. We're done with quarts. So our quarts normalization, I'm going to write them down here on the bottom, is equal to 39.2%. Now I'm carrying to 1 decimal place. I'm rounding as I'm going. Remember I said you shouldn't do that? Because you could, the reason being is because you can end up, you're going to total these, you can end up with 100.1% or 99.9% if you round as you go. And that's fine because that's just a rounding thing. As long as you're not greater than plus or minus 0.1%, you're fine. You don't need to worry about it. You can round as you go. But sometimes you have to go back because I've gotten things that add up and I'll be 0.2 or 0.3% off, and that's too much. So you got to go back. But you're going to see me add these all together when we're finished. So we got our quarts. We are done. Quarts is good to go. All right? We can plot this. We're done with quarts. We can plot that on our QAP diagram. And all we do is we go from the bottom, which is 0. So quarts is always from the bottom to the top. Or if you're using the voids, it's from the top to the bottom unless you flip it, whichever's easier for you. But for QAP, quarts at 0 is on the bottom and 100% is on the top. So you just draw a horizontal line where your percentage is. In this case, it's 39.2%. If you're more comfortable at 39, use that. It's not really going to change the value that much. So you draw your line. So you've got your first line. But I promised I would show you the other example, normalization, to make sure you get this, and that's what I'm going to do right now. I am going to do example 2 to show you that it will give you the exact same 39.2%. Like I said, this is the equation I favor. So let me do that for you right now. Okay, here we are. Here's the second equation. Here, my X initial, in this case, just like before, was quarts. So 29%. Now, I'm going to add, just like I did here, add everything up. And that should give me the 74%, and it does. And I divide that into 100. Now, the reason why I do it this way is because it's easier to do on a non-scientific calculator. Because you just divide 100 divided by 74 first. In this case, it gives me that number. It's a ratio. All right, and you multiply that by your X initial, which in this case is our quarts initial. And we get, lo and behold, 39.2%. 39.2%. So you get the same number using either equation. That shows us both equations are the same. And I already explained to you why that is. Now, all right, cool. We've done quarts, we've plotted quarts. Now we just got to normalize for A and P and plot those two separately, right? No, because this is a 2-point plot, not a 3-point like the USDA textural is. We're only using 2. So we've got to normalize again. Okay. Before I can do my second normalization, I still need to finish my primary normalization. I already have quarts. We're at 39.2%. We've plotted it. We're done with quarts. Quarts is going to be out of it. Now, out of my initial percentages, I had 34% case bar, 11% plagioclase. So I would do the same thing I did for the quarts using equation 2. I'm using that equation 2 here. So I get 45.9%, 9%, and 14.9% for my plagioclase. So these are done. They're gone. We're not going to see those numbers again because we're still finishing our first normalization. So we have these new percentages. Now, do these add up to 100? Like I said, they can be plus or minus 0.1%, but in this case, they do equal 100.0%. Okay, our first normalization is now complete, and I am going to have to do this again because I screwed up the maths, so I'm remaking this video and adjusting for my errors. It happens. But we are done with our first normalization. That is done. We have normalized our quarts, alkali feldspar, and plagioclase. Our quarts was 32.9%. It has been plotted. We are done with quarts. Quarts is out of it. So we're just going to get rid of it. It's done. No more quarts. But we still need to normalize these two. We can't leave these and plot these on the QAP diagram like this. This isn't going to work. We need to set these two numbers to 100%. So how do we do that? Well, first we add them. I'm adding from left to right. Sorry, 60.8%. These are all going to be in percents. I'm leaving the percents off for now. All right, I think you can figure that much out. You guys are a smart bunch of people. You can figure that much out. Okay, so this is going to become my new 100%. I'm going to use equation 2 again. Okay, so what I've done is I've rewritten the second equation here. And same as before, except you have one less thing to add because Q's out of it. So you're just using your alkali feldspar plus your plagioclase, which will be divided into 100, multiplied by either your feldspar, whichever initial you're using, or your plagioclase. And we will get values. I'm going to plug and chug here for you. I'm not going to write on the board and take you through it, and we'll see what we come up with. Okay, so plugging my alkali feldspar initial into this equation. Remember, A plus P is 60.8. We divide that into 100. We actually get this number here. So I'm just going to leave that there and not do this part. So you can see that is derived from this part of the equation. Gives us 75.5%. Now we put our P initial in, and 100 divided by 60.8, and we get 24.5%. So we have done our second normalization. Well, do these two equal 100%? Well, does equal 100.0%. So we don't even have a mess to deal with here. We don't have a 0.1 plus or minus. No, we don't have 100.1. We don't have 99.9. So we got 100%. So those numbers related to this whole are good. Now you got to check yourself, because what I did before was I had a bit of dyslexia transferring numbers, and I can still work it out and get 100%, but if I flip the number, like if I flip this 9 and this 5, I'm going to add this up and get a different number, but if I work through it and don't make any more errors, they're still going to equal 100%. So you got to make sure you don't flip the 5 and the 9. That's what I did, and that's why I'm redoing this video here. Now, before I show you how to plot the last part on your ternary diagram, I need to explain something here. Remember how we did our first normalization? We got a bunch of numbers, but we only plotted the Q, the quarts. All right, we got 32.9. Now, if you were to take this after you've normalized twice and look at these, you might sit there and think, whoa, shouldn't those equal 100%? No, they shouldn't. These two need to equal 100% after your second normalization. This is already done. It's been plotted. It's out of the calculation. All right, so how am I going to show you how to plot this? Well, as you already saw from our first normalization, 32.9 is our quartz. I took all the granites, tonalites, all that stuff out for now because I'm just showing you how to plot these last two numbers, because you don't just do what you did here, because this is 0 for quartz and this is 100%, and you just draw a horizontal line up. Here we're about a third of the way up, 32.9%. All right, that's what we did. But you don't do that for these two, all right? Because this is not a 3-tier plot. I'm going to use green. Okay, so we're going to plot these two simultaneously. Okay, so you basically at the top you just put a big dot there. All right, you can think of this as a pendulum. We're going to do something like a pendulum action here, a swinging motion. And if you're using the FAP diagram and you flipped it over so it wasn't upside down but looked like this, you'd still put it there. If you want to leave it upside down, you would put our dot there and you would swing it like this. But here, we're going to swing it like this. So this point doesn't move. Now, what do? Well, we have 75.5% alkali feldspar. This is 100% alkali feldspar. This is 0% alkali feldspar. This is 0% plagioclase. This is 100% plagioclase. So now we've got our locked point. We're always going to do this, no matter what numbers we get. All right. So, but we have 75.5% alkali feldspar, 24.5% plagioclase. So we can go either or. We can either use this one or this one, but we're going to plot them both simultaneously. I'm going to use alkali feldspar. So I'm going to go in, remember this is 0 alkali feldspar, 0, this is 100%. I'm going to go in 75.5%, roughly 3/4 in from my 0. And I'm going to draw my line. It'll actually be 75.5%. Sorry about the sloppy line. But there's my alkali feldspar at 75.5%. Coincidentally, if I were to go from 0% plagioclase to 100 and plot this one instead, my plagioclase. Now I have 0 to 100% plagioclase. I would go in 24.5%. It's the same line. It's exactly the same. So you can use either or and it would swing. So that's all you have to do. Where they meet, right here, that is your classification on your chart. If it's a granite, if it's a sinogranite, if it's a monzogranite, whatever it is, that is your number right there. And that's it. You don't need to worry about a third line. You don't need to worry about a third point. Because quite honestly, you know, the USDA is awesome for its own right because it's a little normalization. The maths are simpler. But the more lines you start plotting, the more you can mess things up. They may not cross. You might get confused. And you got to go back and do it anyway. So that's the advantage to the system. And why do we do it? There is a reason why we do it this way. This can be turned into a pyramid or three-dimensional plot. But yeah, that's something totally different. And here's one of my books. So this is my stuff. I'm taking this from here. So where does this plot? Since I screwed it up before, I'm going to show you this. Okay, you can see there's a QAP plot right there. And if I did plot this, I do not have it subdivided. You saw the earlier slides where granite was subdivided. Here it's not. Because you can stop right there. This rock is a granite. And usually you can stop right there. But you can divide a granite into a sinogranite and a monzogranite. Sinogranite's to the left, monzo's to the right. Well, what's the point of this? Well, the point of that is if you're in an area like the Pinokian orogeny, where you have a lot of these similar granites in northeast Wisconsin, like the Spikehorn Creek, the Bush Lake, the Amberg, Esthaline, you need to divide it out a little better because they'll have variability, but it's easier to talk about them that way. And in this case, this is going to plot specifically as a sinogranite, which is granite. Is there a faster way to do these calculations? Honestly, the answer is yes. So why did I show you this way? For a couple of reasons. The first one being, as I already stated, I wanted someone who's not mathematically inclined to be able to do these normalizations. The other reason is because you may not have a scientific calculator at your disposal, so you're going to have to do these steps. But yes, there is a quick, fast way to do this, but I'm not going to go into that at all. I wanted to do it this way. There's a third reason too, so I could take you through the actual steps as you plot. The third reason of me doing this is because I wanted to take you through the plotting as we go along. I didn't want to sit there and do a bunch of maths for you and then plot a bunch of stuff and you're like, wait, what goes where? So that is it. If you have any questions, comments, need clarification, caught another error of mine, please let me know. I hope you learned something.